Okay, so we can say that the angular impulse of f about point A is equal to integral frp dt. And since rp is constant, we take it outside of the integral. So the angular impulse of this force is rp times the linear impulse of the force I. Now, at the final state, you have plastic collision and your system will stop. They said that your system will collide with the box, and due to plastic collision, it will stop there. So omega 2 is equal to 0. Okay. Now, so you got your first equation. Concerning the number of unknowns, we don't know the impulse and we don't know RP. We have two unknowns here. That's why we need to come up with another equation in order to solve for RP. That's why here we can apply the not only the angular principle of angular impulse and momentum, also think about linear impulse and momentum. And sometimes if you apply the angular impulse and momentum principle and you still have unknowns, think about applying the principle of linear impulse and momentum. If we do this for the following system, if we consider x direction, okay, what do we have in x direction? They want us to design the system in a way to not have this horizontal force. So ax should be 0. Okay. So if you look in x direction, the only force is F. Okay. So if we apply linear impulse and momentum in x, you have mvg1 in x plus summation of integral f dt. The only force doing an impulse is F, so it's just integral f dt, no need for summation, equals to mvg at state 2 in x direction. But as you can see here, we are in the case of rotation about fixed point A. So at this position, at the position of collision, which is the vertical position, vg vector is horizontal. Okay. And because VG is horizontal, then it's already along x, no need to project. We just have to replace VG by its value. And since we have rotation, okay, so VG can be written in magnitude. It's equal to R omega in magnitude, but since it's directed in negative I, so I can say that VG1 vector is minus the mass, is minus r bar, which is the radius of rotation, since the distance from G to A is r bar, times omega. So now if I replace in my equation, the linear momentum mvg1 is minus mr bar omega 1 plus integral f dt. Integral f dt is the impulse I, equals to, at final state, we said omega 2 is 0. So since omega 2 is 0, Vg2 will be equal to 0. So my equation, this equation will help me to get what? To get the expression of my impulse I. I is equal to minus m times r bar times omega at state 1. Okay. So now, if I go back to my previous equation and I replace the linear impulse by minus mr bar omega 1, okay, I did use the following. I can take into factor omega 1. I will have first the inertia about A. In order to calculate it, you know that you need to apply the parallel axis theorem. So it's mkg square plus m times the distance from A to G is r bar plus m times r bar square omega 1. Now for this term, okay, you replace in this equation integral f dt, which is I. You replace it by its expression that you got from the linear momentum. So you will have minus mr bar omega 1 times rp equals to 0. If you simplify omega 1 from both sides, you can get the expression of rp you divide the whole terms divided by mr bar, and you take rp to the other side. So rp is equal to this term over m times r bar. So the expression of rp that will give me horizontal force of 0 is m will be simplified, is kg square over r bar, and the plus r bar square over r bar is r bar. So this is the design that will lower that will give me the lower impact in x direction at point A. Okay. Question on this?
دكتور وين طريقة التتا يلي كانت بالجيفن الصورة فوق؟ ليه بس تعبناها أبدا ورسمنا الفيجر ستريت؟
اوكي، لأنه نحن عم نشتغل just before and after الcollision. اوكي، لأنه what is happening انت the collision force F is due to impact. يعني انت you are working at this position. اتفقنا؟ هلا كيف فينا
Yes.
نعوز التتا؟ التتا فينا نعوزها لو مثلا ما معنا اوميجا 1. يعني هون in this problem اذا بدك هلا اوميجا 1 اخر شيء صار عملت simplification. بس in case مثلا you want to calculate omega 1 فيهم يعطوك ال initial angle, you apply conservation of mechanical energy بين ال initial position وال position just before impact تتلاقي الأوميجا 1. اوكي؟
اوكي دكتور، وفي جي نحن حطيناها to the left انه هيك we assumed it.
لا مش we assumed it. ما انت كيف عم يبرم البندلم؟ مش clockwise؟ انت بالvertical
clockwise.
position كيف this is your where is G? G is here. G is here. إذا أوميجا clockwise كيف بتكون في جي؟
كمان.
to the left. ما هيك؟
Yes.
اوكي.
اوكي دكتور، واخر سؤال، الامبلس كيف طلعت نيجاتيف؟ ما هي minus mr omega 1 plus impulse equal لزيرو.
اوكي، مش الامبulse منا نيجاتيف. الامبulse is in positive x direction. اوكي، بس انت هون عندك وقت كتبنا الايكويشن انت عندك المومنت للاف. انتبه على شغله، المومنت للاف باي دايركشن about A؟ يعني F is in positive X ميشيل، بس المومنت تبع about A is counter clockwise. وانت بالانجلر مومنتوم كيف اخذ البوزيتيف دايركشن؟ clockwise. يعني الانجلر impulse is negative. يعني اللينير اذا بدك اللينير impulse positive بس الانجلر impulse negative.
اوكي thank you.
welcome. other question
دكتور
on this؟
هتعملي ابلود لهيدا الفايل على على
أكيد.
التيمز؟
اكيد I will
اوكي
send
ميرسي.
you the files. اكيد.
اوكي ميرسي.
انتم معكم لحديت ال 18؟
ما بعرف صراحة، عم شوف انا 19.
اوكي.
نحن
yes
معنا
دكتور،
كتاب
انه
معكم يا ميشيل I sent
نحن
it to you. I
معنا
sent.
كتاب لدكتور قديم.
اوكي ليكو هيدا ال 19. هلا اذا
yes
ما عندنا
دكتور
اياه
I sent
هلا
them
ببعث
to the
لكم اياه اذا
class.
ما معكم اياه. ومن بعد هون حنكمل. انتو في عندكم البي دي اف البي دي اف الداينامكس from previous years حنكمل فيه. اوكي، اذا ما عندكم اياه انا ببعث لكم اياه. Okay, so now we discussed how to apply the principle of angular impulse and momentum. A very important application of this theorem is in case summation of angular impulses is zero. So if the summation of external impulses is zero, we can apply conservation of momentum. Okay? مثل ما في conservation of linear momentum إذا linear impulses are equal, summation of linear impulses, external impulses is zero. كمان فينا نعمل conservation of angular momentum if summation of angular impulses is zero, of external forces. Let us consider the following. فإذا when we said when the summation of external linear impulse are zero, L1 equals L2. And now this is conservation of linear momentum. The same apply in angular momentum. So if sum of external angular impulses is 0, then hg1 equals hg2, and we say we can apply conservation of angular momentum, which is the case in majority of problems. يعني هلا we'll see together that in a lot of problems you have that summation of moments about a certain point is 0, so you can apply conservation of angular momentum. Let us consider the following example. We have a 10 kilogram wheel that rolls without slipping and does not rebound. So we are in rolling without slipping condition, and it will not rebound, يعني it will not lose contact with the floor. We want to find the minimum velocity Vg the wheel must have to just roll over the obstruction at A. So what do we have in this problem? We have first a disk doing translation, okay? So initial motion is translation. When we reach, if we don't have friction with the ground, velocity will remain the same. So we reach, we have a certain velocity before collision in horizontal direction. Vg1, okay? Now, what will happen during collision? They are saying that because of collision, what will happen is that the disk will rotate about A. We have rolling without, since we have rolling without slipping and no rebound, will not lose contact with A. And the disk will be like, will do this. It will go over A, then it will move downward and continue its motion. So no loss of contact with A, okay? So in order to do the analysis of this problem, we need to divide it into steps, translation step and rotation step, okay? So since no slipping or rebounding occurs, the wheel pivots about point A. So the force at A is much greater than the weight, and since the time of impact is very short, the weight can be considered as non-impulsive. So whenever in a problem, they give you collision, and they don't give you the time. And here you will have a collision at A, then the disk will rotate about A before moving back to ground. During this collision, we don't have information. We don't know delta T, okay? So we have just to consider that because delta T is really small, the weight, the force, the normal forces like the weight that are not directly affected by the load can be considered to be to have negligible impulse, okay? And we'll see how. So since no slipping or rebounding occurs, the wheel pivots about A. The force at A is much greater than the weight, and since the time of impact is very short, we can consider the weight to be a non-impulsive force. Then the dominant force is the reaction force at A, but the problem here is that we don't know the magnitude or direction of A. This is why to overcome this problem, what should we apply? We can apply conservation of angular momentum about A. Because if you do analysis of forces during the collision and during the rollover about point A, what are your forces? So you have when your disk was here in contact with A. You have the normal, when you rotate about A, you have contact, let us draw it exactly. So the contact now will be with A, okay? And forces are the weight and the contact forces at A, and you can have friction and normal. And since friction and normal are passing by A, so they are not producing any moment about A. The only force doing a moment about A is the, if you want, is the weight. But the weight is non-impulsive, because here during rotation, the weight will not always pass by A. Let me show you a figure to clarify this. This is the figure. When you approach point A before starting to roll over, the weight is at this position. So you have a moment for the weight about A. But since the weight is non-impulsive, it's very small compared to the impulse force, then you can neglect the angular impulse of the weight. Okay? And you can apply conservation of angular momentum about point A. Now, actually, what is happening? Before the collision with A, the motion was translation. And you know, in translation, how you calculate the value of angular momentum about any point? You can do
The general form.
exactly. During translation, أول شيء omega 1 was 0 because it's translation. So no rotation. Okay? So you just have to take the moment of mvg1 about A. To do this, you have mvg1 times this distance, which is the distance between sorry, guys, 1 second. You don't have translation of the disk here. You have rolling without slipping. Okay, there is a difference between the two. To have
General plane motion.
yes, it's general plane motion. To not have omega, okay, they should tell you that you have pure sliding. If you have pure sliding, then you don't have omega. But here, since it's rolling without slipping, you have angular velocity omega 1, and you can relate omega 1 to Vg1 by, since you have rolling without slipping on the ground, you can say that Vg1 is equal to omega 1 times times the radius of the disk. Okay, now so you have to account for two terms when you calculate the angular momentum about A. You need to account for Ig omega 1 plus the moment of mvg1 about A, and to consider mvg1 moment, you have mvg1 times distance from G to A. This distance, this perpendicular distance, okay, 1 second bus to put to annotate. This is the perpendicular distance of interest, okay, which is equal to the radius of the disk minus this small height here, which is given in the problem to be 0.03 meters. So you need to add two terms. You need to add the Ig omega 1, which is the effect of rotation, plus the moment of the linear momentum about A, which is mvg times this distance. This is how you can get the total angular momentum at state 1. Now, at state 2, what is happening? When you collide with A, suddenly, okay, you will transform the type of motion. Yani now, the disk was doing general plane motion. Now, after collision, it will do rotation about A. So it will rotate about A, okay? And the question, the purpose is to find what should be the minimum velocity to be able to overcome A. Yani you will rotate about it and then you can move down. To be able to rotate about A, you need to be able to reach this position. Why this is the most critical position? Because here you have an elevation and you gain potential gravitational energy. Okay, so at this point, at this level, you will have the minimum velocity. So you need to solve your problem into several steps. You need first to study collision, because once you study collision, what do you find? You can find omega 2. And once you find omega 2, you can say, to be able to overcome A, I need that my initial velocity omega 2 should be high enough to give me gravitational potential energy at the maximum height position. We'll do this in steps, but now forget the work about potential energy. Let us stay in collision. In collision, what will happen? You will transform your motion from general plane motion to rotation about a fixed point. Okay, so because now you are rotating about fixed point, just after collision, what will be your velocity? since you rotate about A, your
Omega
velocity
R.
cannot be horizontal anymore. It should be perpendicular to AG. So you know that at state 2, VG2 is perpendicular to AG. And you can say that I am now rotating about point A. So I can do two things, or I can replace HA by IA omega 2, or also I can use the general form, which is the moment of linear momentum about A, mvg2 times the radius, plus ig omega 2. Both will give you the same result, because what is vg2? Vg2 is the radius times omega 2. Okay? When you do this, you will be able to relate the angular velocity before collision to the angular velocity after collision. Okay? So this is the first step in your problem, to relate your two angular velocities.
دكتور انت
نعم. Yes.
قلت اي اي اوميجا 2 او شو؟
أو general formula. شو هي general formula to calculate angular momentum about A؟ هي linear momentum، هي moment of linear momentum about A. And since VG, MVG at state 2 is perpendicular to AG, يعني what is the linear momentum? MVG2 times AG.
اوكي
يعني إذا بترجع بتعمل البارallel axis theorem بترجع بتوصل ل IA أوميجا.
ارجع لهذا يعني هي عادة هي المومنت تبع اللينير مومنتم بلس الكومبوننت
plus
اي
IG
جي
omega, exactly. Okay. So now we got a relation between omega 1 and omega 2. So we can deduce the relation between VG1 and VG2. But the question didn't end here, because we don't know VG1. The question is, what is the minimal value of VG1 that will allow us to turn over A? Yani we need to reach the most critical, if you want, position. What is the most critical position? You need a minimum velocity to allow you to reach this position here, for which G is at a maximum height. Okay? Because when you want to roll over A, the level of G will increase. Because look, at the initial figure, what is the elevation of G? It's the radius of the circle.
0.2.
Okay, it's the radius, 0.2. But when you want to go over the pivot, so let's say this is your pivot, okay? You want to roll over it, your disk will be in this position now. And what will be the maximum height for G then? It will be the radius plus what?
Plus 0.3.
Plus the height here, okay?
0.06.
So you need a minimal velocity, because to be able to reach this position, what is the minimum velocity here at the maximum height? 0, okay? So in order to reach this position, you should at least have velocity of 0 here, okay? To reach just a velocity of 0 here, the velocity before should be able to the change in kinetic energy should be able to compensate the potential energy. Okay, so you can say, to find what is the value of VG1 minimum, I need to apply conservation of mechanical energy between the position just after collision and the maximum height here. Okay, why I can apply conservation of mechanical energy? Because during the rotation, okay, A is fixed, so the forces acting on A will not do any work. The only force doing work is the weight of G. So I can apply conservation of mechanical energy. And the minimum velocity just after collision will be the one that will give me a final kinetic energy equal to 0. Yani the whole kinetic energy will be transformed into gravitational potential energy. Okay? So let us see this in detail. If we go back to the figure, this is the position just at the end of collision. And now what will happen? The disk will rotate about A until reaching the maximum height of G. To be able to do this, you need a minimum velocity VG2. in order to reach this critical position at a velocity Vg3 of 0. Okay, if you have Vg2 larger than this minimum velocity, then you will reach the maximum height with a velocity different than 0. But the minimum velocity, and to be able to reach this position, you need at least to reach it with 0 velocity. Okay, so all we have to do is to apply the concept of conservation of mechanical energy between these two positions, between position 2 and 3. So first, we have a kinetic energy at position 2 is what is the kinetic energy at position 2? Can you tell me?
half mvg2 squared.
No. Why it's not only half mvg2 squared? Who remembers?
في
لأنه
rotation طبعاً.
rotation
لأنه عندنا
فبنعمل
rotation.
rotate.
Exactly. You know that in rotation, I need to. So what is the general formula for kinetic energy? You can use two
half
formulas,
mvg
or half,
squared plus half ig
yes,
alpha.
or half
sorry.
mvg2 squared plus half inertia about g omega 2 squared. Or what can you apply here because you are rotating about A?
نستعمل
half
I
IA omega squared.
Exactly. So, or you can directly say, since I rotate about a fixed point, I can replace T2 by half I inertia about A times omega 2 squared. Okay? So now, what will happen then? You have to find omega 2. So at state 3, what do you have? T3 is 0. Now, concerning the potential energy, you know that for gravitational potential energy, we need to select a datum, a reference. So you can, if you want, consider that the datum is at position 2. The datum is passing by G at position 2. So what will be gravitational energy at state 2? 0. And
0.03.
what is the gravitational energy at state 3? It's just
0.03.
mg times which height? يعني G will undergo a certain elevation. What is this elevation? It is the height here of the of this small element here. Okay, so you need to say that at state 3, V3 is mg times this is small height h, which is 0.03 meters. Okay, so now in this equation, your only unknown is omega at state 2. So you will be able to solve for omega 2, and you will be able to find then what this is omega 2 minimum to be able to reach the maximum height. So, and since omega 2 is related to Vg2, you calculate Vg2. And from the first step of conservation of angular momentum, we were able to relate Vg2 to Vg1. So in this way, we can solve for the minimum velocity Vg1 in order to be able to overcome the obstacle. Okay? Any question on this problem? Okay. Another example.
بس بفكر سؤال
نعم.
في شغلة صغيرة ما انتبهت لها بالأول ليش عملنا 0.2 minus 0.03
لأنه
0.03 شو؟
يلا لأنه أنت بدك تجيب المومنت of MVG about A. Let us look at the figure. أنت مش عم تعمل رفيق مش عم تعمل angular momentum about A.
لا
Okay. يعني you need the distance for the linear momentum MVG from A.
okay.
Which is the radius minus the height of the obstacle. Okay.
Yes. وبالإيكويشن نحن كتبنا إنه W1 هي VG1 على R.
Yes. أكيد. لأنه rolling without
Okay.
slipping. Yes. Okay.
Okay.
Another problem, a 5 kilogram slender rod shown in the figure is connected with a pin at O and is initially at rest. So omega 1 is 0. If a 4-gram bullet is fired into the rod with a velocity of 400 meters per second, as shown in the figure, determine the angular velocity of the rod just after the bullet becomes embedded in it. Okay. أول شيء, the bullet will be embedded in the rod. يعني شو type of collision?
Inelastic.
Plastic, okay? Because when the two bodies will move at one final velocity, يعني the problem is a plastic collision. So the bullet will stick to the rod and it will be part of this rigid body. Okay? Now, they want us to find what is the angular velocity just after collision. This is the question. Okay? طيب. In this problem, if we want to do the analysis, what do we have? First, the bullet will reach the initial state. The bullet is in translation. And it will reach this point with a velocity of 400 meters per second. So the velocity can be decomposed into two components, one in x, one in y. And the rod has initially omega equal to 0. Okay. Whenever you have collision, you can think or about linear momentum or about angular momentum. But if you want to apply linear momentum, you need to solve for what? You have reaction at O or X. Okay, that is unknown. So since the reaction at X is unknown, if you do linear momentum, you will add an unknown to your equations. So it's better to start with angular momentum. And what is the best point to do angular momentum about?
O.
Oh, why O? Because in the position of collision, okay, the bullet and the rod, the bullet weight and the rod weight will be passing by O. And OX, OY are also passing by O. So what is, during collision, what is sum of moments about O? If we take system bullet plus rod, all forces are passing by O. So sum of external moments is 0. So what can we apply then? We can apply conservation of angular momentum about point O. Okay? So since we can apply conservation of angular momentum about O, let us do it first. Okay? We need to determine at the initial state, what is the angular momentum of the rod about O? The rod is rotating about O. Yani the formula for angular momentum about O is I-O omega rod at state 1. But the rod is not rotating. It's initially at rest. Yani the angular momentum of the rod initially is 0. Now, what about the bullet? The bullet was in translation. Okay? So we can say that the angular momentum of the bullet about O is the moment of its linear momentum about O. We have two methods here. The first method, if we don't want to decompose VB into X and Y, we just have to find the perpendicular distance from O to VB. And geometrically, it's easy to find it because we have that this distance here is 0.75. And we know that this angle is 30 degrees. So this one will be 60. And this one will be 30 here. So the distance from O, the projection distance here, is simply 0.75 times cosine 30. So, and we know that what is the angular momentum of a particle about the point? It's the moment of the linear momentum, يعني plus mvb times the distance d, where d is 0.75 cosine 30. Okay. Now, if you don't want to do this, if you want to project, you have two components for your force, X and Y. بس ال y component is passing by O. Can it produce any moment about O?
No.
No. يعني what is the angular momentum? هاخد ال direction of angular momentum counterclockwise, positive. Okay? So your angular momentum will only be the one for VBX. And since MVBX will cause a counterclockwise moment about O, so I can say that the angular momentum is plus mass of bullet times velocity of bullet in X times which distance? This distance, the perpendicular to VBX, which is
0.75.
0.75. And actually, we get exactly the same result because what is VBX? If you project VB on horizontal line, VBX is VB cosine 30. So we got exactly the same result. Okay. So this is the initial angular momentum of the particle about O. Since we have conservation of angular momentum, this is equal to, at the final state, we have one rigid body. So the particle will be a part of the rod. So we can say that the system will rotate about O. So we can say it's equal to IO total times omega at state 2. Okay. Now, how to find the total inertia of our system? Our system is divided into two parts. You have the rod and you have the particle here. Okay. You know that for a rod attached at its extremity, what is the inertia? 1/3
over 3 ml squared.
ml squared. While for a particle, what is the inertia of a particle about a point? It's the mass of the particle
half mr squared.
times the distance, exactly, times the distance from the particle to O. يعني here the distance is from particle to O is 0.75. يعني plus mass of the bullet times 0.75 square. This is how you calculate I total. The only unknown in your conservation of angular momentum is omega 2. You can solve for the value of omega 2. Okay. So in this way, we can
دكتور
find, yes?
بس لقيت تاني ميثود إذا بنقسمها للإكس والواي الفي بي، ليش حطيت الفي بي هي البوينت على الرد ونحن مش عم ناخدها إنه بيفور، يعني كانت بعدها فوق، يعني عندي
لا
واي.
ميشيل، انت just before collision، بس هون وين بتكون البارتيكل؟ هون. اتفقنا؟ انا وقت حطيت
اوكي.
اللاين هون، وقت عملت المومنت، ما اذا you displace a force along، if you displace a vector along its line بيتغير المومنت about O شيء؟
No.
لا. فاكتشلي انت وقت توصل just before الكوليجن وين كانت البولت؟ كانت هون. يعني انت الفيلوسيتي كومبوننتس هن هيدا في بي اكس وهيدا في بي واي، بس في بي واي is passing by O no moment. يعني you just have to compute VBX moment. Okay?
اوكي دكتور ميرسي.
Welcome. Any other question? Okay guys, we are done for today. See you next time. Bye.
دكتور
Yes?
Thank you. Bye.
Yes رفيق.
في أسألك سؤال بالريفيو بروبلم
ايه اكيد. اي chapter؟
19.
Yeah. بلشت في رفيق، اذا بدك بعت لي واتساب لانه we still have less than 1 minute. Okay.